Let's go and take a look at lesson 4.2, linear approximations and differentials. In this section, we emphasize the derivative of a function, and this idea of linear approximation means we're going to use the equation of the tangent line to represent the function. So it's an important concept and idea in mathematics that we can find a simple equation, a linear equation, right, that's related to the original more complex function. And so in this quick example that you see here, the function f of x is 1 over x. It's a rational function. It has issues with domains, right? It's a curved graph. You have the two pieces with asymptotes. And what we can do with derivatives is find approximations for that function at given points. So at a equals 2, we can use this formula, which is just the equation of the tangent line. It just looks different. And so I want to emphasize that this equation here can basically represent f of x equals 1 over x. We can use that to get values for f of x equals 1 over x near x equals 2. And that's why you see 2.1. This value 4.75 from this linear approximation. That's the idea. It's an approximate value for the original function. It's close enough that we can use that we want to use the more simple functions or equations that we get from approximating f of x. And so the same thing here as we go farther away at 10, right? We came up with the equation near x equals 2. As we get closer to 10, these values are not very close to the original value. And that's what we see here. Look at the zoomed in part here. This is the equation. Look, notice that the blue and the orange are almost identical. That this equation represents that near 2. I could use the blue equation to give me that answer there. And so again, this is just a more zoomed in approach to this. Notice this is the big, it looks identical. And then we get close to 2 and move out to 2.1. You can see there's a little difference between the approximation and the function. And this is what we're going to call later differentials as we look later on. But that's what this L equation is. It's basically the equation of the tangent line at a given point. It's just been simplified for us, or we call the linear approximation, or again, the tangent line approximation at some value. So square root of x, right? We can see the square root of x, sorry, there it is. At x equals 9, we know the square root of 9 is 3. So again, we can simplify that, but this function, right, as an example, square root of x is a complex equation, complex function. We find the equation of a line here, and now that represents the square root of x near x equals 9, near it, okay? Because at the 9, I know the answer is 3, I don't need to approximate, but 9.1, instead of finding the square root of 9.1, I can just substitute into the linear approximation, and you get an answer that's very close. You get an answer that's very close to the square root. That's the powerful thing that we're doing here as we're trying to approximate complex equations, functions, with a linear approximation. And it even works for trig functions in this example here. We can calculate the approximation at a certain point and then approximate that function using the linear approximation. So I want to make sure we emphasize that idea again, that it's very powerful that we are able to notice again, right at this point at 1, for the sine x, we have this equation here that's basically identical to the sine x. And that's also what happens, remember, at 0 when we have the limit of sine x over x equals 1, because they're almost identical as x approaches 0. They're identical graphs. So that leads us to differentials. And the differential comes in this picture. We'll come back to it here. The differential is here you have your linear approximation. You see L of x, y equals L of x, and you have y equals f of x, the original function. And so at this point, here is the equation of the tangent line. And then if you move off of that just a little bit from x, right, I still want to approximate the blue function using the orange function. Now, when you do that, right, when we do that, you go over a little bit and you go up a little bit, right? And to get that answer, you will see that's the the notation above, which we'll look at. But we call that dy, that distance from this point to the point on the approximation. It's called your dy, because this is the derivative. So we're looking at the change in x and then the change in y of the derivative function of the linear approximation. Delta y is the distance from the function, right, from this point to this point. Notice there's a little difference in there, and this is going to be what we call the error, right? Our approximation is off just a little bit, right, of the rate and change, how much it increases from x, from this point to this point, how are the y's increasing? Again, the notation looks pretty complex, but that L is our linear equation. It's the tangent line. And so that's what that represents there. And so let's go back to the notation. It's important to take a couple minutes to read that, right? We're used to seeing dy, dx, and before it was a form of the equation here, the derivative y with respect to x, but now we have a meaning to it. Before we didn't break it up, but now there is a meaning to it. Notice again, you can rewrite these functions, right? And they're related. And so there's a relationship between, right, the dy, the differential in y, and the derivative and the differential in x. Those are called, again, differentials, dy and dx. So notice the differential y is a function of both x and d of x, that difference, the x value and, right, whatever the x value is, and the differential somehow determines that, right, because it's from the equation of the line. And so your practice here, and it may not make too much sense what we're doing because we're not applying it, but again, that delta y is with respect to how much the change is made from 3 to 3.1 from this function. Notice we just plug in the values 3.1 and 3, and that's the change in the y. Now the differential is related to the tangent line. If I go from 3 to 3.1. And so we can see the difference using delta y, the difference in the functions, 0.81, and then approximating it with the f prime of x times d of x, which we have a substitution because we know the derivative, and we get the dy, the differential in y. And they're very close. So again, looking at the rates of change, that's what the differentials are doing for us. How much is the value changing from one point to the next point? That's really close to it. And so we can use the actual function, the more complex one, or we use the simpler version, the differential y equation. It's a, again, simpler function to use than the more complex ones. And that's the idea, even though you may think this is not complex. That's what we're doing. And that distance is that error, right? Because when we do approximate, right, the delta y and the dy, we're saying are approximately the same. But there is a distance between them. I go back to this, right? There's a little distance here that would be our error, and that's what you're calculating when it's talking about calculating the error. And again, the functions may look a little scary or not, but again, it's the idea of what you're calculating. I want to remind you again, use my notes or the videos, but I remember I had the notes from our inside of our modules, right? Homework notes. You can go there and take a look. Hopefully my notes are helpful if the videos aren't. And so that would be it.